Okay, here I want to do a little bit of feedback to the exam for BI308, and what I wanted you to do is really choose two statistical tests here, use some illustrative examples, and compare these two tests that you have chosen. And I wanted you to particularly pay attention to the hypothesis that you need to use for this test, how you can apply this test, what is the data format, what are the limitations, and what this test actually is going to tell you. So let's quickly revise what the steps are that we need to do when we use a statistical test. And it's very, very important in the first place that we choose the test depending on the data or the observations that we made. That is the crucial point. This dictates how we proceed. The next step is that we need to formulate a null and an alternative hypothesis. And these hypotheses are incredibly boring. They are really formulaic phrases. It's not like a scientific hypothesis where I say, for example, men are taller than women or something. That's a scientific hypothesis. Statistical hypothesis is something very different, and we will come to that in the next section. We then need to choose what is generally known as a significance level. This is the alpha, that's the significance level, where we then say that's sort of the cutoff point, where we then say, right, we accept or we do not reject the null hypothesis, or we do reject the null hypothesis. We then use our data and observation, and we calculate a test statistics. And different tests do that in different ways, and we have discussed that in the lectures, how you can calculate these test statistics. What we then do is we take this test statistic, and that's the important point for statistical testing. We take this test statistic, for example, a t-value, a chi-square value, a z-score, or something like that, and then we calculate the probability of observing exactly this particular value for the test statistic, or an even more extreme value, and we calculate the probability assuming that the null hypothesis is true, that the null hypothesis is correct. The null hypothesis, that is what we formulated in step 1. And then based on this probability that we have calculated and the significance level from step 2, we then can make a decision whether to reject or not reject the null hypothesis. In a way, we can never really accept a null hypothesis. We just simply say we have no evidence of not rejecting the null hypothesis. I also wanted you to say something about a p-value, and again, to make this very clear, a p-value is the probability for the observed test statistic, or an even more extreme value, assuming that the null hypothesis is true. And we can also write this in a sort of a shorthand. P-value equals the probability for this test statistic given, and that's this vertical line here, given that the null hypothesis is true. And as for any probability, the p-value must be smaller or equal to 1. And it can only be must be larger or equal to 0. 0 means it is impossible. 1 means it is absolutely 100% possible. There is no other chance. So the p-value can only be between 0 and 1. A p-value of 2.8 or something like that simply does not make sense. So what are the tests that we would usually perform? And as I said, it is the data and the observations that dictate what test we use. So a very common test would be the t-test here. And in a t-test we have the independent data, that's the data that we choose. These would be categorical data or nominal data or something like that. We'll just simply have a category. And for a t-test, we can have a maximum of 2 categories. We can have 1 category, or 2 categories. We cannot do more than 2 categories with a t-test. The dependent data, that's the data that we actually measure, that we observe. They need to be continuous. So they need to be, for example, fractions or something like that. And in particular, they are interval or ratios, and that means that they are equidistant from each other, and that this distance actually means something. So I know that 2 is 2 times larger than 1, and 5 is 5 times larger than 1. So that's very important. We also assume that for a t-test that the population from which the samples are taken, that this shows more or less a normal distribution. So that is also called parametric, because it is a normal distribution. And we measure the parameters of the population. And the t-test we would use when the sample standard deviation or sample variance is not known. Now, a z-test is a very similar thing. It is basically exactly the same. We would apply a z-test under the same condition of a t-test. The really major difference is that in this case we have more information about the population and we don't need to make any estimates. So that means the population standard deviation is actually known, unlike the t-test. So that's the main difference. The sample sizes for both can be really anything that we care about, although the rule is usually for a z-test we want to have a reasonably large sample size, so usually more than 30 observations, more than 30 data points, whereas the t-test is a little bit more relaxed. In contrast to these tests, where we use continuous data as the dependent observation, we have the chi-square test. And in the chi-square test, our independent data are again categorical. They don't need to be restricted to 2 categories. They can be more. That's absolutely no problem. The dependent data, the observations that we make, these are actually discrete data. They are not continuous like in the T or in the Z test. They are discrete data, so they could be either frequencies or counts, where we just simply count how often something happens. The nice thing about the chi-square test is that the population does not need to be normally distributed, so it can be parametric or non-parametric. And if you wonder, chi-square test, what this is all about, some of the tests that I showed you actually are modifications of this chi-square test. So for example, a binomial test, where we look at ratios, where we compare two or one or two ratios with each other, that is actually a sort of a modification of a chi-square test. And the same thing for a Poisson. For a Poisson test, where we compare count data, where we have count data, this is also a modification of a chi-square test. Both binomial and the Poisson test then use the chi-square distribution to look at to compare the test statistic that we calculate with with a distribution. So we really distinguish between these three tests: t-test, z-test, and chi-square test, and they really are chosen on the basis of the data that we observe.